Good morning, students. In the coordination chemistry today we will discuss about the bonding in coordination compound. So today's our topic is bonding in coordination compound. In bonding in coordination compound we will study about the Warner's theory, valence bond theory and crystal field splitting theory. At first we will discuss the Warner's theory. So let's discuss three types of bonding we will study in Warner's theory. Second is valence bond theory and third one is crystal field theory. So let's discuss about the Warner's theory. Warner's coordination theory. Generally in a complex compound, complex or coordination compound, in central metal atom have two types of valency. Primary valency and secondary valency. What about the primary valency? So let's discuss the primary valency or secondary valency. Let's divide it. Primary valency denotes or represent by represent the oxidation number of the central metal atom, and it is always satisfied by negative ligands. Next, it is represented by dotted line. Secondary valency, it represent the coordination number of the central metal atom and can be satisfied by both means negative and neutral ligands. Neutral ligand like water, ammonia, so on. Secondary valency is the non-ionizable. Secondary valency denoted by solid line. At first write down the secondary valency denoted by solid lines. Third difference between secondary valency and primary valency is Number 3, Primary valency is ionizable. Primary valency is ionizable. It will give ions in aqueous solution. Aqueous solution means it present in ionization sphere. Secondary valency is non-ionizable. Number 3. Number 1, number 2, number 3. Secondary valency is the non-ionizable. Because it is present in coordination sphere. So as we know, the complex present in the coordination sphere does not give the ions. Next is the secondary valence. Primary valence is non-directional and does not contribute in a structure, whereas secondary valence is directional and it is responsible for the geometry of the complex. So next difference between the primary valency and secondary valency is primary valency is non-directional and does not contribute in geometry or structure of the complex, whereas in secondary valency it is directional and is responsible for the geometry of the complex. This is given by the Warners. Next we see what Warners find out the complex formula of the complex on the basis of primary or secondary valency. So Warners take the cobalt chloride and ammonia and treated with excess of silver nitrate. So we take cobalt chloride and 6 molecules ammonia and treated with silver nitrate in excess. Next experiment, cobalt chloride treated with 5 NH3 and silver nitrate in excess. Next one is cobalt chloride 4 NH3 and treated with silver nitrate in excess. Number 4, cobalt chloride treated with silver nitrate, 3 molecules ammonia, silver nitrate in excess. So let's see what happened. Cobalt chloride provided chloride ion, silver nitrate provided silver plus, and this chloride and this silver react to form silver chloride. So how many silver chloride he found? He found the number of silver chloride is 3. That means in this reaction cobalt chloride gives the 3 chloride ions. Similarly, in this case second one, the number of AgCl means 2 chloride ion is dissociated by this particular cobalt chloride. In case of this particular compound, one silver chloride form means only one chloride ions given by this chloride, cobalt chloride, and in this case no silver chloride formed. On the basis of this, he found that depending upon the nature of cobalt chloride, how much chlorine it releases or donated, so the number of mole of AgCl form. It is, if it is releases 3 moles of chlorine, so 3 AgCl form. If it releases 2 moles of chlorine, 2 AgCl form, so on. Through this experiment, Warner represent a structure. So through this experiment, Warner's capable to represent structure. Represent a structure of complex compound in which both type of valencies are same. So at first, cobalt 3 ionizable chlorine here. That means cobalt NH3 6, because 6 NH3 here. So coordination secondary valency is shown by the neutral ligands, and 3 ionizable chloride shows that this is present in the ionization sphere. So in this way he can successfully form the formation of complex structure of our complex compound. Next structure, and how much it is satisfied by the primary or secondary valency. So let's see here, cobalt is a central metal atom and 3 primary valency is present. So 3 primary valency, suppose one primary valency is here, it is stated by dotted line, one here and one here. So 3 chlorine satisfied by primary valency, because the oxidation number of cobalt is +3. So as we earlier discussed, primary valency satisfied the oxidation state of central metal atom, and the 6th number of amine means coordination number is represented by dotted line, and it is called the secondary valency. So 1 NH3 here, 1 NH3 here, 2, 1 is here, 3, 1 is here, 4, or 1 is 5, and 1 is 6. So in this way he can explain the structure as well as the formula of the compound. Let's see the structure of second compound, cobalt chloride 5NH3 means 2 ionizable chloride. So let's see the structure of second. So in the second structure, cobalt chloride, cobalt and NH3 is secondary valency is 5, and only 2 chloride is ionized, and here is a 3. So means 1 is present under the coordination sphere and 2 present in the ionization sphere. So in this way you can easily draw the structure. Suppose this is the central metal and to the primary valency. So let's represent like this, to primary valency like this, and 5 and 6 secondary valency. So 1 here, 2, 3, 4, 5 and 6. So dotted line represent the secondary valency, dotted line represent the primary valency, and dark or solid line represent the secondary valency. Let's see the structure of or formula of third conditions. In the third, only one ionizable chlorine. So let's we discuss cobalt and NH3 is 4 and only one chloride ionizable, that means 2 chlorine, 2 chlorido present inside the coordination sphere and only one present in the ionization sphere. So in this way you can easily draw the structure of particular compound. And the last one, there is no any ionizable chlorine, so how can we draw the structure? Simply cobalt and how much NH3? Amine is 3 and no ionizable chlorine is all the 3 chloride present inside the coordination sphere. So on this basis, number of times this type of questions were asked. On the basis of this, draw the structure, and on the basis of this structure, write the formula, so on. So it is little important, but it is important for the examination point of view. Let's we discuss the valence bond theory. So, valence bond theory. Simply, at first we describe the what is valence bond theory. Before we discuss the valence bond theory, at first we discuss about the ligands, which is very much important in this particular chapter. So, students, before we discuss the valence bond theory, at first we discuss the limitations of Warner's theory. So let's we discuss write down the limitations of Warner's theory. Number 1, it cannot explain why coordination compounds are formed only by some metals. And it can't explain secondary valency decide the geometry of the complex. Decide the geometry of the complex. And next one is, it cannot explain the magnetic and the optical property of the complex. Of the complex. These are the limitations of Warner's theory. Let's we discuss the valence bond theory. Valence bond theory. Write down the following points. Following are some main points of this theory. this theory. Number 1. The central metal atom makes available makes the requisite number of orbitals to the incoming ligands for the formation of coordinate bonds. For this, the central metal atom undergoes hybridization. For this, the central metal atom undergoes hybridization. This hybridized metal the central metal atom makes available the requisite number of orbitals to the incoming ligands for the formation of coordinate bond. For this, the central metal undergoes hybridization. And the next points, these hybridized vacant orbital may overlap with the orbitals of ligand containing lone pairs of electron to form metal coordinate bond. Metal coordinate bond. If the central metal atom containing central metal atom containing unpaired electron then it will be paramagnetic in nature. The type of hybridization next one is the type of hybridization and geometry of complex can be decided on the basis of its coordination number. Decided on the basis of its coordination number. Suppose coordination number is coordination number is 2, then hybridization SP and the geometry linear. Coordination number 4 So there will be possibility of two type of hybridization, sp3 and dsp2. sp3 tetrahedral and dsp2 square planar. Coordination number 6. Suppose coordination number is 6. So there will be two types of hybridization, sp3d2 and d2sp3. When sp3d2 and d2sp3, in both the case the geometry will be octahedral. So let's discuss about the ligands. Further, ligands can be classified ligands. So we simply divide the ligands into three types: weak ligands, average ligand or strong ligand. Three types of ligand we will discuss. So at first, weak ligand, average ligand and strong ligand. So let's discuss which type of ligands will be strong and which type of ligands will be weak. So weak ligands are poor electron donor, never pair unpaired electron. For example, halogen like fluorine, chlorine, bromine, iodine, sulfide and thiocyanide. Average ligand sometimes it behave as it can act, it is a average electron donor and it can act as a weak as strong ligand. It can be as well as strong ligand. It can act as a weak as well as strong ligand. For example, nitrite in water, amine, ADTA, OH, so on. In case of a strong ligand, it is good electron donor and it will always pair the unpaired electron. For example, unpaired electron in the central metal atom. Most common is CO and Cn. These two are strong ligands. So here note down one point. If carbon donor and nitrogen donor and oxygen donor, three donors are given you, how can you decide which one will be more strong donor? So simply less electronegativity, more the tendency to donate electron. So carbon donor is more electron donor in comparison to nitrogen, in comparison to oxygen. Simply we can say that on the basis of less electronegativity, more strong donor. So in this way you can simply classify the types of ligands with the properties of valence bond theory. Properties. First, it gives idea about the hybridization. Next, gives idea about the magnetic moment of the complex. Means we know the formula of mu equal to n plus 2, where n is the number of unpaired electron. Number 3, it gives the spin multiplicity. Spin multiplicity means unpaired electron. And it is given by the formula. We know that spin responsible for atomic structure is S, so 2s plus 1. On the basis of, we can find out the presence of unpaired electron and gives the spin multiplicity of the particular complex. If one unpaired electron, then the value of S is half. Suppose if one unpaired electron, then the value of spin multiplicity will be half. If two unpaired electron, then the value of spin multiplicity is half plus half, means 1. In this way you can calculate the presence of number of unpaired electron, the spin multiplicity of the complex. And next one is number 4, magnetic nature. On the basis of presence of unpaired electron, you can find out the given complex is paramagnetic or diamagnetic. On this basis, we can find out the properties of the particular complex compound. Let's we discuss by example. Suppose we have a complex compound K4 Fe Cn6. As we know, Cn is the strong ligand and the central metal atom is Fe. This is the central metal atom. So find out the oxidation number of central metal atom at first. So oxidation state +4 for this, plus X, and carbonyl is -6 equal to 0. So simply we can find out the oxidation state of central metal atom is +2, means here is in the +2 state. So let's write down the configuration of Fe2+. Simply by using inert gas configuration argon 3D 6 and 4s 0. So write down the orbital structure 1, 2, 3, 4 and 5. This is 3D. So total how many? 1, 2, 3, 4, 5 and 6, and 4s is empty, 4s 0 and 4p is also present. So as we learn about the ligands, it is the strong ligand and it has tendency to pairing the unpaired electron. So it paired the unpaired electron, so it comes here and it comes here. So it becomes 1, 2, 3, 4 and 5. So 2, 2 and 2, 6. 2 empty orbitals is available due to this particular ligand, because this ligand is strong ligand and this has tendency to pair the unpaired electron, and 4s and 4p. Now the 6 Cn make the bond total 6, so 6 orbitals is available for the complex D2 and the hybridization is D2sp3. So on this basis you can find out the all information about this complex. At first, what will be the hybridization of this compound? So it is D2sp3. And what will be the structure of this compound? So structure is octahedral. Octahedral. How many unpaired electron? No unpaired electron. So this the nature, magnetic nature is the diamagnetic. Magnetic nature is a diamagnetic because there is no unpaired electron. And how can we find out the magnetic moment of this particular? So magnetic moment is also depend on the unpaired electron. So m equal to n plus 2. So here is no unpaired electron, no unpaired electron. So it comes 0 Bohr magneton because the unit we use Bohr magneton. And what will be the spin multiplicity? Spin multiplicity also depend on the number of unpaired electron. Spin multiplicity. So multiplicity we know 2s plus 1 and no unpaired electron. So spin multiplicity will be 1. So in this way you can find out the information about this particular complex compound.